Alright, so hello everyone and welcome to my video poster. I am Jan Tristram Acuña and I'm a PhD student at CISA and I'm currently affiliated with the IFPU in Trieste, Italy. So in this video poster, I will present our work on the phenomenological consequences of an interacting multi-component dark sector. And this presentation will mainly be based on the paper that my collaborators and I published in Physical Review D. So in that paper, we studied the following template for a multi-component dark sector model, and we assessed its viability when confronted with limits on cosmological observables and direct detection limits. So in this setup, we have multiple dark fermions, which are collectively denoted by Q in this case, and these dark fermions are charged under a dark ion gauge interaction. This dark ion gauge interaction is mediated by a massless dark photon. So apart from this gauge interaction here, the dark fermions can also talk with standard model fermions through portal interactions mediated by these heavy scalar messengers. As one can see, the structure of these portal interactions actually provide a way to classify the dark fermions as well as their scalar messenger counterparts. So for instance, we have this lepton-like dark fermion, which only talks with standard model leptons, while we have these dark quarks, which only talk with standard model quarks. In addition, one may observe that the heavy scalars can be further classified according to the chirality of the standard model fermion they couple with. And finally, we have these left-right mixing terms, which generate chirality changing processes. So overall, we see that this setup provides us with a class of models where a particular model is realized by specifying the couplings, the portal couplings alpha L and alpha R, the gauge coupling alpha D, and the masses of the particles that reside in the dark sector. Of course, whenever we encounter a model of the dark sector, we should be able to extract definite predictions in order to compare them with what we know about the universe. Specifically, constraints on our setup can be obtained from precision physics, collider physics, and astrophysics. By combining these constraints, we have the following reference framework for the mass hierarchy of the species in the dark sector. In particular, self-interaction limits from ellipticity constraints on halos imply that the heavier dark leptons should contribute dominantly to the matter relic density, while the lighter dark quarks should contribute negligibly. Now, as one can see from this list, bounds from cosmology and direct detection are missing, and this is actually the primary goal of our work, to supply the constraints on our setup from the point of view of cosmology and direct detection. So in obtaining cosmological constraints, we need to compute the relic density contributions of the stable dark species. And in order to do so, one must first write down the Boltzmann equations that track their number densities. However, we note that our setup has this peculiar feature, which is the fact that we have two reservoirs. So we have the dark sector plasma and the visible sector plasma. And in general, these two plasmas can have different temperatures. And so when writing down the Boltzmann equations to numerically compute the relic densities of the stable species, we have to track not only the co-moving number densities of the dark species, but also the temperatures of the two sectors. However, in the interest of time, I will not go through the details of setting up the coupled Boltzmann equations, and I invite the interested audience to refer to our paper for further details. Instead, I would like to focus on a selection of results from a scan of the parameter space of the model. So firstly, I note that here we are assuming only two dark quarks in the setup, and these dark quarks only couple with the up and down quarks of the standard model. Of course, we have the lepton-like dark fermion and the dark photon. So here on the left panel, we essentially have a projection of n effective limits on the alpha L MQ plane. So n effective is the number of relativistic degrees of freedom, which I take to be at the CMB epoch. Alpha L is the portal coupling. MQ is the common mass of the two dark quarks. So note that here we have translated the limits on n effective to bounds on this temperature ratio Td over T, or C. And we note that the central value for this C coming from the n effective limit is 0.54. These green and yellow bands correspond to 1 sigma and 2 sigma limits respectively, while this red band over here corresponds to the 3 sigma limit and beyond. The white regions correspond to cases where the temperature ratio at the CMB epoch is below 0.54 and are thus allowed under the n effective limits. So as an example, if I take the portal coupling to be 10 to the minus 3, and if we can tolerate the 1 sigma limit, then the dark quark mass can be at least 2 GeV. So this plot over here suggests that for a given portal coupling, we have a lower bound on MQ. On the other hand, we have this additional constraint that the dark quarks should contribute negligibly to the Redox density. And since dark quarks annihilate mostly to dark photons, one can show that their Redox density contribution is proportional to the square of their mass. So then, from that statement, one can see, or one can show, that we should have an upper bound on MQ. So combining these two results lead us to conclude that we have a window of allowed values for MQ. So for the remaining time, I would like to discuss what direct detection can say about our framework. So note that the dark lepton is the dominant dark matter component in our setup. However, the dark lepton does not directly couple with the standard model quarks. And here, you're assuming that the main driver for potential direct detection signals is dark matter-nucleon interaction. So since we're considering dark matter-nucleon interactions here, then the interactions occur at 1-2 level, at least at 2 leading order. And one can show that the dark matter-nucleon interactions can either be standard model photon-mediated or dark photon-mediated. And furthermore, one can show that these vertices can be described by effective dimension 5 dipole and effective dimension 6 charge radius operators. Now, while both mediators give rise to long-range interactions, one should note that for the gamma-mediated case, we have coherent long-range dark matter-nucleon interactions, and the recoil rate scales as z squared over ER, where z is the atomic number of the nuclear target, while ER is the recoil energy imparted on the nuclear target. In contrast, for the dark photon-mediated case, the long-range interaction is sensitive to the spin of the nucleons, and hence this is incoherent when summed over all nucleons. So the long-range contribution to the recoil rate can be swamped by coherent terms coming from contact terms in both the dipole and charge radius operators. Since in the dark photon-mediated case, the dipole and charge radius operators can have comparable contributions to the predicted recoil signal, we first take an agnostic stance and first treat the operators to be independent, since in our framework, the dipole and charge radius operators are correlated. So by first assuming that these operators are independent, we derive direct detection constraints from null results in Xenon 1-ton and projected limits from Darwin, which is a future generation detector. After doing so, we project our model on the constraint plane. So we perform that kind of analysis not only for the dark photon-mediated case, but also for the star model photon-mediated case. So these blue and red curves here correspond to direct detection limits. This region here is excluded. This region here is allowed. The horizontal lines that you see in both panels refer to projected limits on the dipole operators from precision physics and astrophysics. So the gist of this slide is to tell you that the limits that we get from direct detection are competitive with the limits that we get from complementary probes such as precision physics and astrophysics. So to close this presentation, I summarize the main constraints from cosmology, and for the case of direct detection, I list down the salient points that one must take note of in deriving direct detection constraints on our model framework. So this concludes my presentation, and thank you for your attention. Grazie per la vostra attenzione.